Today we're going to talk about thread synchronization. Hopefully, you have already watched the online videos. If you haven't watched the online videos, I would suggest that you go ahead and get those done, not during lecture. But things that you'll find out there that are important, like what is a thread? Right? Why do we need them? How are they the same and different from processes? How is the life cycle of a thread different from a process? How are they scheduled? How do you launch a thread? How do you launch a group of threads? What's the difference between a joined thread and a detached thread? And what happens when threads share resources that are not synchronized? Now, this last little group here, we're going to actually talk about a little bit today. We'll have it mixed in with our presentation on synchronization. So it's just the rest of it. And I'll mention a few things here and there, but it goes into a lot more detail in the online videos. So let's do the 10,000-foot view. Just in case there's a chance that maybe one or two of you have not seen the videos yet. What are the likelihood of that, right? All right. So, if you have never written a program where you told the program in your code to launch a thread or a group of threads, that means that you have always written serial programs. And that is pretty common. Okay? Basically, the way things work currently, and there's debate on whether it should be this way, but basically the way things work currently is there are two different approaches to writing code: serial or threaded. Threaded programs are a lot more complicated. There's a lot more interaction going on with them. So because of that, the idea was, okay, we'll teach everybody to program serially. And then, assuming that they started, these days in kindergarten or grade school or maybe high school, at some point in time in college, we'll say, hey, the way you've been doing this isn't always going to work, and there's another way. So I want you to completely rewire the way you think about coding and throw away 10, 15, 5, 6, whatever years of this is how I do it. Okay? Now, there is an argument that says, well, we should start writing multi-threaded code from day one. Just keep it relatively simple, but not have to retrain our brains. Well, no matter which side of the argument that you're on, the way that it is now is most of you have never written a multi-threaded code. So what does this mean? If you picture a regular, ordinary computer program, you're just executing a series of instructions, right? That's why it's called serial, one after the other. At any given time, you can only execute a single instruction. Okay? So, you do A, and then you do B, and then you do C, and then you do E, or D, and then E, and then F. Now, you can move around, right? You can use like a go-to and jump from task C to task F. You can do a loop, right? You can sit here and loop between C and D, or just around C, and do that particular one over and over and over again. But at any given instant, you're only doing one thing at a time. Okay? That's a serial program. Now, this thing that we are imagining this running on is actually a thread. A thread is a line of code being executed over time, right? So So this is moving through time. We did A, and then a few milliseconds later we did B, a few milliseconds later we did C, and so forth. Now, when you write a program like this, you're only doing one thing at a time, which means, let's say, for my program to run smoothly, I need to accomplish all of these particular tasks within a certain amount of time. If I don't complete them within that amount of time, the program starts to chunk. It starts to slow down. It starts to basically, hiccup. Okay? In order to keep this going, I have to do them within a certain amount of time. That's true of every single program. Now, when your programs are relatively simple, this isn't hard. As your programs become more complex, these tasks, or the number of tasks that need to be completed within the same amount of time, gets higher and higher and higher. Now, if I want to make this program more complicated, then I either do more things within these individual tasks, or I add more tasks that have to be done by the same amount. Regardless, as long as I can do them all in the proper amount of time, my program runs nice and smoothly. But as my program becomes more complicated, this gets harder to do. So what ends up happening over a 40-year period was that in order for our programs to become more complicated, our processors had to do more in the same amount of time. I had to basically be able to execute this stuff faster. Now, there are a lot of things that influence that. One of the things that influences that in a major way is clock speed. Okay? So in theory, if everything else is the same, and that is an important disclaimer, a 2 gigahertz processor is going to be able to do twice as much work as a 1 gigahertz processor. Now, that is an oversimplification, but if every single other factor was exactly the same, that would be true. The clock runs twice as fast. I do these things on the clock cycle, so I can do more. Okay? And that's what we did. So if I was writing a program and I wanted it to be of a particular complexity, and the typical computer that I wanted to run it on couldn't run it fast enough, well, basically what I did was wait until faster hardware came out. And every year, hardware came out that was faster and faster and faster. Okay? Now, that's all well and good until we get up to about 2006. In 2006 timeframe, there are a whole bunch of milestones to get hit, and one of them is we kind of run into a speed limit. It's somewhere around 5 gigahertz. When you get clock speed above 5 gigahertz, we start to get some quantum physics effects that make it unstable. They're very hot. They burn a lot of energy. So for a whole bunch of different reasons, 6 gigahertz processor, that's a hard thing to do. All right. Well, at the moment, if I can't make a 6 gigahertz processor, what do? How do I make a more complicated program that runs in the same amount of time? Well, that's where we come into multi-cores. That's where we start seeing the first dual-core processors, quad-core processors. All right? The more cores I have, the more things that can be done simultaneously. Right? Each core is working on tasks at the same time. So if I have 2 cores running at 2.5 gigahertz, that's about, air quotes, the same as a 5 gigahertz processor. So that's what we did. And that's when multi-core processors started coming out. Now, that's all well and good, but it presents us with a bit of a problem. If I write a serial program, a single-threaded program like this, and I run it on that dual core processor, it can only run inside a single core at any given instance. Now, that means that if I have a multi-core processor, I can run more programs at the same time. All right? I can have more programs running on both cores at the same time and get that equivalent of 5 gigahertz of speed, but each program can only run in a core at any given time. So again, this helps me with lots of relatively small programs. But it does nothing for me if I have a big program and I want to spread its work out across multiple cores. Okay? I mean, you can imagine a scenario where I have a single core processor that's running at 4 gigahertz, and I have this program on it, and it's running okay, but I want a little bit better performance. And then I hear, oh, they just came out with a dual core processor running at 2.5 gigahertz. That's about the same as a 5 gigahertz processor. I'll buy that, and then my program will run faster. Except it doesn't, because it's a single thread program, which means it's only running in a core at any given time, which means I'm basically running it at 2.5 gigahertz instead of 4. It's actually going to end up running slower. If I want to be able to run multiple things over multiple cores from the same program at the same time, I need more than one thread, because the threads can be scheduled on the cores independently of each other. So what I can do, he said, realizing that the eraser was all the way down here, said Misaka, Misaka. If anybody gets that, good for you. What I can do is say, okay, I'm going to launch a separate thread of operation, and that thread will run out of ink. That thread will run in parallel. And what I can do is I can take something from up here, let's say C, and I can run it on that thread. And now, instead of doing A, B, and eventually getting to C, while I'm running A and then moving on to B, C's on its own thread, running in a separate core. And now I've just done that work in that much less time. So I did more work in less time. Okay. The more things I can put onto other threads, the more threads I have running, the more work that can get done in the same amount of time. Okay. That's the whole idea. The only problem with this is that in order for this to work perfectly, all of these things that I'm doing have to be completely independent of each other. Okay? So B doesn't need or share any resources with A. C doesn't share or need any resources with C. If these things are totally and completely independent, I can put them on all their threads, separate threads, and let them fly. Okay? But that's usually not the case. There are usually some dependencies. All right? So, for example, let's talk about a heavy dependency. Let's say that B uses values that are calculated by A. That is a strong dependency. Basically, B cannot do anything until A is done. So although I can put it onto its own thread, it's just going to sit there waiting until A does its thing. So I've not gotten any advantage, and I've burned extra resources doing it. So it doesn't make any sense to put B onto its own thread. So I would leave B here. Now, let's say C down here is totally and completely independent. It doesn't need any of those previous values. Well, that's a great candidate. I can take it, put it down here, get it processed at the same time, have more done, get to D faster, and so forth. Now, some things can have a relationship that is weak. It means the relationship is there, but because of the nature of the code, and this usually involves shared resources, there are things that can be done. I don't have to sit and completely wait for the other one to be done. I just have to coordinate certain aspects of it. If I have a weak relationship, then that can be put down onto its own thread. All right? So for example, D up here. Let's say D up here has a weak relationship with C. Doesn't matter who the relationship is, but I can take that and I can put it onto its own thread. Because it's a weak relationship, I do need some coordination between these two. That's synchronization, what we're talking about mostly today. Right? But there are other things going on. This D does more than just that part that needs to be synchronized. So the other stuff can fly. It can do what it's doing. I only have to slow things down and synchronize when those particular weak aspects need to be done. So I got this much work that needs to be done in it, and only this much of it actually needs to be synchronized. That's what makes it a weak relationship. And so because of that, I can put it down here, I can get ahead, I can get advanced, and I'll have to wait maybe for some other information, some shared resource to be available, but I shouldn't hopefully have to wait too long, and the length of time that I have to wait is small compared to the amount of time I gained by getting this all done. Okay? Now, there's another aspect. These are different tasks that are trying to accomplish, and I'm trying to get a bunch of them done in as short amount of time as possible. There's another thing that threads can be used for. Let's say that I have something, it's a single task, but with a single thread doing, it takes a long time. So I've got a large piece of data typically, and this thread's job, this task job, is to crunch that data. Right? I can break that task, that one task, into multiple tasks and crunch that data faster. Okay? The easy example is like a render file. You've rendered out this file. It's a big-ass file of data. If you have a single thread working on it, that thread's basically going to start at one end and crunch 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 until it gets through the entire data file, and then it can send it on. All right? That's going to take a while if it's a large file. If I want to do it faster, I can break the job up into multiple threads and have multiple threads working on that file all at the same time. Now, they're not doing different tasks. They're all doing the same task. What they're doing is doing it to different parts of the data. I split the file up into a whole bunch of pieces, and then each thread works on its piece independently, and each one gets through its piece faster, and therefore I crunch the entire file faster. The analogy I'd give first off for this one is, imagine you have a giant leaf and you have a caterpillar, right? And the caterpillar comes in, it's going to process the leaf, it's going to eat the leaf. So it starts at the end and it starts eating and eating and eating, and eventually it works its way and it eats the entire leaf. If I need that leaf processed faster, I get 10 caterpillars. They all surround the leaf and each one eats a different part and the leaf gets done faster. That's what we're doing here. If I was to do that, let's say that's what E is, then I'll launch a thread, and in this case I'm actually launching a thread from another thread. We can do that. But instead of launching just a single thread, I'm actually going to launch 3 threads. And I'm going to call them, what is it, E1, E2, and E3. Each one of these threads is doing the same thing, just to different pieces of the data. Okay. This is the basic threading model. Now, when I started off with this thread up here, and then I added more. The thread up here in C is called main. It's the main body of your program. Any threads that you launch by saying, I want to launch threads, that's these. So if I go in and I write a program and I launch 10 threads, I'm actually going to have 11 threads. There's the one that runs main, and then the 10 that I launched. So you're always going to have one more thread than you launch. And that's an important thing to remember, because a lot of people start trying to figure out the synchronization between all the threads that they launched and making sure that everything's cool there. And they forget that this is also a thread plotting through, and it may require synchronization as well. And if you don't, it's doing stuff before it should. At least that's a possibility. So always remember, main is a thread. So when you launch off the threads and you're seeing what they're doing, don't forget main's still back there doing stuff too. And that may need to be synchronized with the other. Okay? All right. So, synchronization, that's the topic for today, the official definition. And basically, I have tasks that I need to accomplish, and there's a relationship between the task being done by one thread and another thread, or multiple threads. Because of this, there may be things that must be done in one thread before another thread can do something. Or there may be a shared resource between the threads, and if I'm changing that resource, updating that resource at the same time, things can go all out of whack. So I have to take control of that. And that's what synchronization is. It's taking control of different threads and how they interact with each other. Now again, if a thread is totally 100% independent, guess what? You're in luck. You don't have to synchronize. If there's any kind of dependency at all, some synchronization is going to be necessary. If it's a strong dependency, well, you need to question whether you should be doing that at all. But if it turns out it's the only way, then you're going to end up having to do a lot of synchronization. Strong dependencies are something to be avoided at all costs. Dependencies are something that should be kept to an absolute minimum. Because anytime you have to synchronize, you're slowing things down. Okay? In an ideal world, if I'm writing a multi-threaded program, everything divided up onto threads would be 100% independent. I wouldn't have to do any synchronization, and that means that code can run as fast as possible. The minute I introduce synchronization, I slow my code down. Because I'm saying to a thread, a group of threads, hey, stop for a moment. Don't execute anything until something happens over here, and then it's okay to go on. Or, oh, you need this resource. Well, I can't give it to you right now because someone else is using it. You'll have to wait until it's available. There's a way that people try to emphasize things by overstating it. And the mantra for multi-threaded code is, if you have to do synchronization, you've already lost. Now, the idea there is to impress upon you that synchronization is a necessary evil and it needs to be done as little as possible. If there's a way to figure out how to do something, to use a different logic that reduces or eliminates the need for synchronization, that's what you need to do. You don't synchronize things without a good reason. Anything you synchronize that didn't need to be synchronized, you just slowed your program down for no reason. Every time you synchronize, you increase the possibility of a synchronization bug. Okay? So synchronization is not something that we want to take lightly. And we'll go through some design ideas, some problems in the way that people code this stuff that make synchronization a bigger issue than it should be. Okay? So, let's take an example called a race condition. Here's the official description of it. I have an illustration of it that I hope is a little clearer. But the basic idea here is I have multiple threads. The number of threads does not matter. It could be 2 threads, could be 20 threads, could be 1,000 threads. It doesn't matter. Now, when this thing is messing up, the more threads, the more possible ways it can mess up, but it's still going to mess up. The number of threads doesn't matter. And the basic idea here is a shared resource. You have 2 threads that share a common resource, right? In this particular example we're going to use, it's this, where we have multiple threads doing the same task, but with a shared resource between them. And because it's a shared resource, if we leave it alone, bad things happen. Okay? So we have to synchronize it. So, let's look at an illustration here. Now, this shows 2 threads. The number of threads does not matter. We have thread 1 and thread 2. In this particular case, they are running the exact same code. And at this point in the code, what we're doing is incrementing an integer. The integer is initialized to 0, and what's supposed to happen is that a thread comes in, increments it to 1. The next thread comes in, increments it to 2. Next thread comes through, increments it to 3. So basically, we're counting our threads as they pass through this point in the code. There are a lot of good reasons to do that. It's a very simple operation. It's really hard to get anything simpler than incrementing an integer. The only problem is, when you increment an integer, we kind of think of it, oh, it went from 0, it went to 1. But it was actually a multiple step process in there. Things had to happen, and those multiple steps in going from a 0 to a 1 or a 1 to a 2, those can be interrupted, and that's where the synchronization issue is going to come in. Okay? So, I have 2 threads. They're coming through. They're running the same thing. The other thing I'll mention about threads right now, and we talk about it in more detail in the online presentation, but you have no control over when threads will run. You don't have even control over what order they'll start in. So if you write a program, you say, I want to launch thread 1, and then thread 2, and then thread 3, and then thread 4. They're not going to launch in that order. Sometimes the 3rd thread will launch first. Sometimes the 1st thread will launch first. Sometimes the 4th one. The order that they go in is beyond our control. And like I said, the reasons behind that are in the presentation, but that's what it is, and we have to live with it. That means that we can't determine things based off of order. These threads have to be able to show up in any order that they do, and it has to work. It can't break. I can't build it into my code that thread 1 will be there first and then thread 2. I have no way of doing that. Okay? So I've launched 2 threads. up here in the thread in the green box, this is what the threads are doing. They're running the exact same line of code at the same time. So in order to increment, right, we're going to break it up into its stage. In order to increment this from 0 to 1 and then from 1 to 2, whoever gets there first is going to have to copy what's in memory, the value for x, into its local register. So thread 1 gets there, and it copies the value in. And thread 2 shows up at about the same time, maybe at exactly the same time, and it does the exact same thing. And then they're going to increment it. And then they have to write it back and save it. So in this case, and again, the order could vary, but in this particular case, thread 1 finishes first and writes it back. And then thread 2 writes it back. Now, it was supposed to be counting the threads. It should have gone incremented to 1, incremented to 2. But instead, I got 2 1s because they read the 0 value at the same time. Now, what I want to happen is for the first one there, whoever that is, to grab the 0 and nobody else be able to change anything until it writes the 1 back, and then another thread can grab the 1 and increment. That's the synchronization that we want to occur. Now, in this particular example, instead of going from 0 to 1 to 2, it went 0, 1, 1. We probably didn't even notice that it was a different one. All right. If I had 10 threads in here, it could get a lot more complicated. You can imagine a scenario where maybe I get lucky. This probably wouldn't happen, but maybe I get lucky, and the first 3 or 4 threads show up, and they don't mess with each other. So the first one comes in and counts 1. Second one comes in, counts 2. Third one comes in, counts 3. Fourth one comes in and counts 4. All right? I got real lucky. But while that was all going on, another thread had slipped in there and read the value when it was a 1. And then maybe that thread, scheduled on the processor, like a process that's in the online videos, got interrupted and got put into the back of a queue. So instead of running right away, it got delayed, came back in, finished doing the increment, and went from a 1 to a 2. After the first ones had all gone 1, 2, 3, 4. So suddenly my count goes 1, 2, 3, 4, 2. If you have more threads, you got a lot more combinations. If you just take this, and you can in your lab, when you start this, it's uncontrolled, they'll bounce all over the place. You're using letters instead of numbers, but they bounce all over the place. Why? Because different threads are reading them at different points, updating them and putting them back, and so it bops up, it bounces down, because it needs synchronization and it's not synchronized. So what am I going to do about it? How do I synchronize? Well, there are a bunch of different ways that we can synchronize things. The first one we have up there is semaphores, and then in quotations I have mutexes. In a never-ending effort to make things confusing, a semaphore can be different depending upon what programming language you're using. So in some languages, semaphores, C, C++, semaphores are an old school way of doing it that was replaced by a more automated way of doing it called a mutual exclusion, or mutex, what we have in the braces there. That is what C++ and C call it today, mutual exclusion. A semaphore for that environment is an old school way of doing it that we don't do much. So we're not going to worry about it in here. There are a couple of languages out there, though, that they're using a mutual exclusion, but they call them semaphores. So if you're in a particular language, and I believe the most common one is some versions of Java, you'll be working with semaphores, but they're just mutual exclusions. That's just the name they give to them. Mutual exclusions will be our focus as far as controlling and synchronizing our multi-threaded code. It is the modern way of doing it that is most versatile. A mutex can basically be used to synchronize anything. It can synchronize a variable. It can synchronize a code section. It can synchronize an entire function. It can take entire chunks of code and synchronize them. It can be as big or as small as you need it to be. Most of the other things we're going to mention as possibilities as far as synchronization are concerned are built from mutexes. Okay? Now, 2011 was a watershed year for multi-threaded code because C++ 2011 came out. And for the first time in C, there was code that allowed you to write a multi-threaded program in C or C++. Prior to that, if you were coding in C and you wanted to launch threads, you had to do it through the operating system. The operating system launches, controls, and manages threads. It still does. Back then, that was the only way that you could do it. I should say prior to C++ 11. Now, there's a couple of inherent problems to that. The first one would be, if it's controlled and you can only command it through the operating system, that means it's unique to the operating system. So, if I'm writing a Windows program, a Win32 program, I'm using the Win32 command set, and the commands to launch a thread are unique to it. If I want to write the same program and have it run on a Unix-based box, and that includes Linux, I have to use a command set, an API called POSIX. Now, POSIX allows you to control all kinds of stuff, but one of the things it does is launch and control threads. So if I'm writing a program for a Unix or Linux-based box, I use P threads, POSIX threads, not Win threads. The syntaxes are different. The way it's organized and structured are different. Which means if I want to write a cross-platform program, I basically have to have a thing check. Am I on Windows or am I on Unix? If I'm on Windows, go down this branch. If I'm on Unix, go down this branch. Duplicate it all in two different, slightly different logics, different syntax. That writes multi-threaded codings on multiple platforms, a royal pain in the butt. C++ 11 unified all that, and now I can write and launch threads in C using a standard format, and when I compile it, the library, as part of the compilation, will go, oh, I am compiling for Unix. So these are the underlying command sets that this stuff is going to cause me to launch. Oh, I'm compiling on Windows. I'm going to use this. So it allows us to run a single logic, write it once, and then it is changed depending on which platform it's compiled for. That simplifies things a lot. Now, way down underneath the hood, it's still the operating system that's running and managing all that. That's why it's in this course. But we've just simplified our life by being able to use that API. That was the first step. Since then, they have been making improvements, trying to make our lives easier, trying to automate more things. Okay. If I take something that's fairly complex, and I write code that can do it under different scenarios, encapsulate that, and then give it to you as a tool, you put it into your code, you feed it some information, and then it does its thing for you. That is a black box. Right? A lot of code commands that we use are black boxes. One of the things they've been doing since 2011 is in each different release, adding more and more black boxes to make our lives easier. The only problem with a black box, the more complicated the thing I'm trying to make easier, the more general I have to be able to write it, the more branches inside it has, the more versatility it has to be able to do. So basically, I have to be able to handle lots of different types of inputs and ways that it could be implemented. And that makes that black box inside more complicated. The more complicated it is, the more resources it uses, the longer it takes to get the job done. So I make a black box that makes your life easier, but it's going to run slower, sometimes a lot slower. It's not going to be as efficient as if I had coded it myself. Well, the whole reason we're writing multi-threaded code is because we're stretched on resources. Usually time is the most important, but we're not doing this for the fun of it. We're doing this because time is an issue. We want to get more done in less time, and this takes longer to do. So what ends up happening is these black boxes are great, but they're not always useful. Sometimes you can use them and they work fine and your life just got a whole lot easier. Great. Sometimes they're just too slow. They take too long. So yes, your life is easier, but you don't get what you wanted to accomplish. So sometimes you can't use them. The more complicated the thing is that they're trying to do, the longer it takes, the more extra resources it takes. Well, that kind of defeats the whole purpose. All right? Because of this, when you go out there and you start doing research and stuff, you might see some other ways of doing some things, but they might not be that useful to you under your particular scenario. Okay? This next one we're going to talk about is the atomic reference. The atomic reference is one of these black boxes. Everything I said about black boxes and resources does not apply to atomic references. Atomic references are very simple inside, but they're very limited in what they can do. What we're going to do in a moment using mutual exclusions is basically just encoded inside a little black box called an atomic reference. The code's not that much different than what you're going to write. It's not significantly slower. It may not be any slower. It's one of those black boxes that what it does is so simple that it's not a problem. Unfortunately, for our purposes in this class, you can't use them. And the reason for that is some of the things that we're going to have you doing manually, writing your own code with mutual exclusions, is how you learn to use those mutual exclusions. You need to learn them doing simple things so that you can apply them later on to more complex things. And if we used atomic references, you wouldn't get that experience doing the simple things because the atomic reference would do it for you. This next example we're going to show you. Or, well, we already showed it. We're going to show you how we're going to fix it. All I had to do in the real coding world was when I declared my variable x, instead of just declaring it as an integer If I had declared it as an atomic integer, I wouldn't have to do any of this stuff. It would already be done for me. It's already coded inside that. That's why you can't use it. You need to practice with this stuff in simple things so that you can use it when you get to more complicated things. Now, once you get out of this class, feel free. Use it to your heart's content. But all it does is control a variable. You can't use it to control a whole code section or a whole function or a whole area. It just controls a variable. It's nice. It means you don't have to write that little tiny repetitive code over and over again. But that's all it's doing. If it was doing things more complex, then you would have to make a choice of, is this thing fast enough? Does it meet my needs? Like other black boxes. Monitors, a bit old school. Condition codes, we're going to actually discuss that. That's controlling and synchronizing things remotely from other threads. Then compare and swap, that's a bit old school. There's some other stuff out there. What we're concerned about, the most powerful tool in your multi-threaded toolkit is the mutual exclusion, the mutex. Okay? So let's look at that problem again. Now, I've changed my code a little bit. Now, this is pseudocode. I have my two threads, right? Both threads show up, just like before. But I've got a couple of lines of code that I've added in. The code that I've added in is my synchronization. Now, the first thing that happens when we show up, instead of just copying the variable in like I did before, the first thing I do is lock the variable x in memory. Now, both of these are running the exact same code. One of them will get there first. In my example, in all my examples, I go 1, 2, 3, because that just helps me keep it straight. But the order doesn't matter. It works exactly the same. If 2 showed up first, it would work exactly the same. Whoever gets there first runs the lock variable x in memory and puts a lock on the variable x. This is referred to as taking ownership. So I'm taking ownership of this variable. If I have ownership, I am the only one who can manipulate it. If anyone else tries to, if they attempt to take it, they will receive a signal back saying, this is already owned by someone else, and they will get blocked. Okay? So in this case, thread 1 showed up, locked the variable. Thread 2 showed up just a short time later, tried to lock the variable. When it tried to lock the variable, it got blocked. And what that's going to do is take thread 2 and stick it into a waiting queue. Now, this takes it out of the ready queue, so it's not sitting in there just cycling around, going through the ready queue into a core, failing, coming back, going through, failing. It keeps it from doing that. It takes it, sits it on the side in a waiting queue. Other threads would come in and the exact same thing would happen. They would all get put into that waiting queue. The only thread that can run and do anything with this is the one who got there first, thread 1. And then thread 1 is just going to do exactly what it did the last time. I'm going to increment the variable. So it's going to copy it. It's going to increment it. And it's going to write it back. Now, once it's written it back, it's done with it. It's not doing anything else. It's not making any changes in it. So it's going to unlock it. When it unlocks it, that's going to send a signal to all of those threads sitting in that waiting queue and say, hey, that variable you tried to get that wasn't available, it's available now. And then It's a bum rush. All the threads wake up, jump out of the ready queue, jump out of the waiting queue and run to one of the ready queues, jump in the ready queues, work their way through. Someone will get into a core first. The one that gets into a core first locks it, takes ownership. The others, when they get there, find out it's already owned, and they get stuck back into the waiting queue. Yes, sir?
Is there any way that two of them could get to it at the exact same time?
It is a mathematical possibility, and I believe that basically if it was to somehow occur, it just kind of flips a coin as to who gets it. All right? But it's remotely, like it'd be very unusual. It is always a possibility. It can happen. If it does happen, though, it's not going to break anything. All right? Now, the thread that gets into a queue and gets through its queue and gets into a core first takes ownership. That blocks all the others. And again, it's going to do the exact same thing. It's going to bring it in. It's going to increment it. It's going to write it back. And when it writes it back, once it's done with it, it's going to unlock it. And the same thing's going to happen. If there are more threads waiting, they'll jump up, jump into the queues, run through the queues. Whoever gets in there gets it. The others get blocked. And this keeps happening, rinse and repeat, until all of them have gone through. Okay? Yes, sir?
Do you have access to the queues of which ones are running and which ones are not running? Which are like waiting?
That data is monitored by the system. You can query the system and get that. Yes?
When threads are in the waiting queue, does that mean that they don't do any processes and they just wait? Okay, so
yes.
They're not like running other things while they're waiting. They just...
No. Now, we have ways that we can do other things, but in its basic form, and in that case, they would not go into a waiting queue. They'd go somewhere else. If they're in a waiting queue, they are stopped. They are doing nothing. That's why we say, if you're synchronizing, you're slowing things down, because all of those threads are now idle. Right? That brings up a good point here, though. If all this was doing was this, there'd be no reason to write this as a multi-threaded program. Right? Because even though I'm launching more threads, even though I'm burning more resources, they're only running this one at a time. I might as well have just written it as a serial program and not had the complexity. But the idea here is that this is a small, tiny part of a much bigger operation. So yeah, I'm doing it one at a time here. I've kind of gone temporarily back into a serial mode. But there are other places where we can be running full tilt and doing things simultaneously. So I'm only doing it at this point in time. And the speed advantage I'm going to get is going to be in those other areas of the code where it doesn't have to be synchronized. So that's what we're doing with synchronization. Let's look at the components that we're going to use. The first is a mutual exclusion, a mutex. Okay? It is defined in C++, C, in the header mutex. So if you're going to be using mutexes, you have to add the mutex header. It is a synchronization object. Right? It has two states. It's either locked or it's unlocked. That's it. Now, this is the basic form. Depending upon how I lock it, I can get different behaviors But it will always be just either locked or unlocked. The behaviors are around how it's locked. It itself is just either locked or unlocked. Okay? This is only going to lock a single thread, single object at a time. All right? If I have a thread, thread 1, and it locks something, and a different thread comes up and tries to lock it, it will get blocked under most circumstances and get put into that waiting queue. If I was to loop around and the same thread that has already locked something loops, comes back and tries to lock it again, that will generate an error. And it doesn't generate a, hey, you tried to lock something that you already own error. It basically generates a, oh no, something happened type of error. In general, it won't let you compile. Well, let me change that statement. Sometimes it won't let you compile, but sometimes it will. And you won't be able to actually see that it's a problem until you run the code. Okay? You typically see this in a circumstance where some of the ways that we can lock this are automatic. In that I can say, hey, let's lock this thing, and then when I'm done with it, it exits a particular scope, and that causes it to automatically unlock. Okay? There are only certain ways of locking it that do that. Understanding that scope is important. Knowing exactly when and under what circumstances it automatically unlocks is very important. This error where you're trying to lock something that you already own usually happens because you locked it, you thought the scope had exited, so it had automatically unlocked, you go to lock it again, but you misunderstood the scope, it never unlocked it, so now you're trying to lock something that it still owns. That's usually when you see it. Okay? So we said we're going to lock it, and we get different behaviors depending upon how we lock it. The first way that we can lock it is with a lock. This is the basic, most simple way to lock it. All the other forms are built off of this, right? So this is the first Lego brick. The lock command is going to lock it. The corresponding command to unlock it, oddly enough, is unlock. Okay? So I lock it, do my stuff, and then I unlock it. This form of lock is totally, completely, 100% manual. If I lock it, I have to explicitly say unlock it somewhere. If I don't, it will remain locked. Okay? Now, this does present a little bit of an issue for us. Imagine, if you will, that you've got a function, and somewhere at the top of it, you lock some lines of code. You do the lines of code, and then you unlock it. And your program comes in, it starts executing, it hits the lock, it locks everything, it starts running the code. Before it's done, before it gets to the unlock, it throws an exception. Bang, just threw an exception. It exits out of the function, calls cleanup, goes into move into some sort of recovery. Maybe it goes and tries to lock that function again so it can re-enter, right? Except you never unlocked it because you never got to the line that said unlock it. So you recover, you go to re-enter the function, and you try and lock it, and you already have it locked it, and that means error code, because you tried to lock something you already locked. That's another way that that can happen. If you're going to write recovery, right? Or even if you're not going to write recovery, you just want other threads to have access to this. Because remember, it's still locked. If this thread's sitting over on the sideline, it's still locked. Other threads can't get in. They're still sitting in that waiting state, right? If you want to prevent that, and you need to, you have to cover yourself. The easiest way to cover yourself, it's not hard, you just have to remember to do it, is you write an exception handler that says, hey, if I throw an exception, unlock this. That's it. It's not hard. Now, that's with these basic forms of locks. In a little while, we're going to talk about automatic locks. You don't have to do that with them because they will automatically unlock themselves under multiple scenarios, one of them being if an exception is thrown. But if you're just using the basic lock form and you want to cover your butt, and for our labs, you have to cover your butt, it's a point deduction, you need to have an exception handler in there. Yes, sir?
Do you get an error for calling unlock on a variable that's already unlocked?
No, that will not generate an error. Well, let me change that statement. It will not generate an error that is going to blow things up or anything like that. It will generate something internally that says, hey, you tried to do this, but it's not going to be fatal. All right, so here's an example of code. Now, in the videos, we talk about this without the mutexes, and if we were to just run this, okay? This is just a little program based off of the Hello World program that everybody writes when they start writing C, but we've written it in a multi-threaded format. And so what's going to end up happening is I'm going to launch a group of threads, and that group of threads is going to go and run the function hello world. And inside, all they're going to do is print out hello world with some other information. Now, if I do not take control, if I just write this and run it without any locks or anything, the monitor is a shared resource. If it's not controlled, a shared resource is accessible by everyone at the same time, which means all of the threads who are running this code and sending it to the monitor are all sending it to the monitor at the same time. So all the lines will get jumbled and mixed between each other. Okay? It'll look like gobbledygook. Right? It's all messed up. We're going to use a lock to synchronize it so that each line prints out the way that it's supposed to. Okay? So, starting up at the top, way up there, I have included thread. Why? Because I'm launching threads. IO stream, because I'm throwing stuff to the screen. Vector, because I'm launching multiple threads, and I use the vector for that. And then mutex, because I want to control it. Now, the next thing you'll see there, I'm declaring a mutex named mutex1. Mutex1 is a name. It can be anything. Bob, Larry, Susan. It's just a name. Okay? You'll also notice that I am declaring it globally, so I can use it anywhere in my code. This is not considered good programming practice. We do not typically want you to declare your mutexes globally. We want them to be local. Now, it does complicate things a little bit, because if you declare it, for example, in main, and you want to use it inside a function, you have to pass it via reference. So if you're rusty on your C pointers, brush up, because you're going to have to move things around via reference using pointers. That's probably in the first week, that's probably where most people struggle, is remembering back and trying to dust off those gray cells that cover pointers and so forth. Okay. I got a short little example code here. I don't want to overcomplicate things, so I'm going to cheat. I'm going to declare it globally so I don't have to worry about it. We will show an example in the class where we don't declare it locally. All right, so let's go ahead and start off in main. Now, there are multiple ways to launch threads. You can launch a single thread by just launching the thread. That's covered in the video. You can launch a group of threads, but when we launch a group of threads or a pool of threads, we typically want a way to manage them as a unit, okay, as a group. In order to do that, I need some sort of data structure to hold the information about them so that I can manage them as a group. This could be done, for example, with an array. But we actually have a type for vector for controlling threads. So the preferred method is to launch your threads and push them into a vector and then use the vector to manage them. And that's what we're doing here in this next line. So I'm going into a loop. Oh, excuse me, let me step back a second. All right, so going into main. First thing I'm going to do, I'm going to create a vector for threads, so it's for type thread. And I'm going to name it threads. Again, this is a name. I'm calling it threads. Could be Henry, whatever. Now, I'm going to go into a loop, and basically I'm going to loop through 5 times. Each time I loop, I'm going to launch a thread, and I'm going to push it back into threads. So my command here, standard thread, that's going to launch the thread. Now, I can just launch a thread and not do anything with it and give it a job or a task to do later on. Or I can go ahead and give it a job to do right now. In this particular case, I'm going to tell it, go run the function hello world. Now, because I've declared my mutex to be global, I don't have to pass it via reference. If I hadn't done that, though, I would need to do that here, where I'm telling it, hey, go run this. All right? Loop through 5 times, launch 5 threads, put them all into the vector, point them all to hello world. Now, I've launched 5 threads. How many threads are running? 6. Remember, main is still running, and we have to consider that. Okay. So before we track what's happening with the threads that I launched, let's see what happens with main. Now, main launched all of those threads, and then the next thing it does is run this little thing here, this little chunk of code here. And you'll notice it's a thread join. What's that all about? A join is a synchronization method. Okay? When we launch a group of threads, they are given a status called joinable. Okay? This is a temporary status. They cannot stay in this status. If I was to launch a group of threads and not tell what kind of threads they are, the compiler will error, usually. Although occasionally it will let you get away with it, in which case it'll blow up when you run it. That joinable state is an undefined state. Its behavior is unpredictable. And it certainly won't do what you want, but it's going to blow up one way or the other. You are required to change its state to something else. There are 2 other states, joined and detached. I'm doing joined here. the characteristics are different depending upon whether I make a thread joined or detached. Okay? So the way that we visualize this, we have some thread. In this case, it's main. Doesn't have to be. But we have some thread, and we're launching another thread just like we did before. Right? But this thread is going to go off, and it's going to do stuff. If I declare this thread to be a joined thread, that means I am joining the parent and child together. That means that this thread that I launched will return to the thread that launched it. The child will return to the parent. If it's been calculating values, it will bring those values back and make them available to the parent. Okay? So this is one way that I can access. Let's say I threw this off to calculate a whole bunch of variables that main wants to use. Main was doing other things while that was being calculated. Right? And let's say that main doesn't need it until it gets into this part of its code right here. So I'm doing the calculations. Main is doing its thing. Now, I can't run this without these variables. So this has to be done before I can run this. If I've joined the thread and I put the join right in front of where I need it, what's going to happen is when main hits this point, the join, if this is already finished and has brought the variables back, it will grab the variables and keep on trucking. It won't wait. On the other hand, if main gets here and I'm still calculating the values and I haven't returned yet, main will pause. It will wait right here until I do return. And then it'll move on. And that's all automated. Okay? Now, once a thread is declared to be joined, that's what it is. It cannot be changed back. It can't go back to joinable. It can't go back to, go to be into dispatch. It's just a joined thread. Not dispatched, detached. Right? All right, well, a couple of different ways I can use this. The example I just said, I need values from it. Okay, that's cool, that's cool. What if I don't need any values from it? Well, I might take it and put it at the very last line of main, and therefore main won't stop until all the threads are finished. That's kind of what I'm doing here, except slightly different. Or, what if I have to do something here? It doesn't actually use any of the variables, but I want to make sure that this is done before I do this. I can use a join. That is actually what I'm using it for here. Okay? Because if we look at the next thing, I'm going to print out to the screen, press enter to continue, and then wait for a character to be hit, and that'll end the program. Main, if it didn't have this, would launch the threads and print this to the screen, either in front of or in the middle of what the other threads were doing. By putting this join here, I'm basically saying, finish doing that, return, and then I'll print this. Okay? Now, if you diagram this, it kind of looks a little weird, because what's actually happening here is I'm putting the join immediately after, and I'm not doing anything, so I'm launching off a group of threads and coming back to exactly where I launched, and I'm waiting there. But again, this is a very simple example, all right? In a real world sort of scenario, a main would probably be doing other things. So the join would be down here. But the join goes where you want main or the thread that's the parent thread, to wait. Okay? We cool on that? All right. Well, if that's what the join does, oh, and by the way, the command that does this is just join. The rest of this is basically it's just a little chunk of code. You can steal it. I did. This is a little chunk of code that says, hey, all those threads in that vector I'm managing as a thing, join them all. All right? That's all it does. Now, let's say I launch a bunch of join threads. When I do that, there's extra overhead involved. I have to monitor information about the threads that I've launched. I have to monitor information about main. I have to track all that stuff so I know when they come back. All right? And I have to have a way of getting that info if there is info. By the way, I can bring stuff back, but I don't necessarily have to use it. I can use it for synchronization alone. All right? But I got stuff I need to track, extra stuff. And one of the things we're going to repeat over and over in this class until you're probably tired of hearing it is that small increases in resources, and never forget that time is a resource, small increases in resources that don't seem very big, if you're doing something millions of times per second, it adds up. Okay? So if I'm launching all this stuff and I use a join, there's going to be a little more overhead, a little more resources needed to manage it. Now, if I'm doing a small number of threads, or I have to have this synchronization, that's the price I pay. But there are some threads that I might launch where I don't give a flip. I don't need anything back from them. I don't need to synchronize them. I need to release them, let them do their thing. The first thing you know about them then is that they're totally independent, because otherwise they'd require synchronization. So if they're totally independent, I let them fly, they do their own thing, they end when they end. And as long as it doesn't affect my program, why waste time tracking them? And that's what a detached thread is. Now, the rules are slightly different on a detached thread. On a join thread, we put where we want them to come back. In a detached thread, they're not coming back. Now, technically, you can say this thread is detached anywhere, right? But let's say I launch them here, and I remember to put it when I'm writing code down here, and so I say that they're detached down here in the code. 6 months later, when I come back, I'm be looking at those launch threads and going, are those detached threads? Are they join threads? Now I'm doing a search to see what they are. So logically, typically, I launch them, I detach them, boom, right there in the code. Compiler doesn't give a crap, right? Compiler reads all and puts it back together in its own image. But for my own sanity, I usually launch them and say they're detached. Now, if they're detached threads, they fly off. Let's say I have a bunch of them. They do their own thing. When they get to the end of their code, they end, and they are cleaned up by the operating system. Easy peasy. A good example of a detached thread. Communication daemons. So communications daemons manage communications typically on a large server. By the way, it is daemon, not daemon. The daemons are threads. Typically, a thread launched as a communications daemon can control 1,000, 5,000, whatever connections to that server. It's basically saying, like a phone operator, old-timey, you ever see an old movie? It's like plugging them in. Oh, you want to talk to the database or you want to talk to the game? Here, MMO, back-end server, anything that's handling connections, usually off the internet, they're using communications daemons to do that. You're probably going to launch thousands of them. Well, the more I launch, the more those extra resources would add up. And I don't need to. Because they're launched from the primary program, they do their thing, connecting people in. If the primary program goes down, there's nothing to connect them into it. They error out, and they get cleaned up by the system. There's nothing else for them to do. They don't need to come back. They don't need to bring any data. They're just plugging in the connections and jumping through them, managing them as they go. So I can save a lot of resources by making them detached. If main goes away, if it crashes or whatever, doesn't matter. There's nothing for it to connect to, so they don't have any purpose now. They'll all be shut down. They'll all be cleaned up. When I restart main, they'll be recreated. That's a good example of detached. Now, when I took over this class 6 years ago, I looked at a lot of operating system textbooks. And I discovered that there are a couple of people out there who are writing operating systems textbooks who don't fully understand how operating systems work. And they give bad advice because of it. And this is a good example as a programmer why it is important to understand how the operating system works. When we write a program, we are typically concerned with the internal logic of our program. All right? The logic I create, the world I create inside my code for my program, that's usually what we're worried about. But my program is going to run in a different realm controlled by somebody else. It runs in the operating system. And what the operating system does and the rules that it follows have effects on my program. Now, they can be very minor. A lot of them there's nothing you can do about, but understanding how they work sometimes is important. So here's the example. We say that one of the things that's low-hanging fruit as far as launching threads are something that takes a lot of time, but it's not essential to what's primarily going on. All right? That's something that's pretty darn independent, probably totally independent. Well, there's a thing out there that fits this perfectly, and that's writing a log file. Now, I write a log file. That means I'm writing it out to a hard drive or a solid state drive. Those devices are very slow compared to everything else going on inside the CPU and the cores and all that. That's all flying at the speed of light. Writing out to even a solid state drive is a relatively slow, lengthy process. If it's a hard drive, mechanical hard drive, it's even slower. So this is a perfect opportunity to say, oh, we'll launch that onto its own thread, and it'll write this stuff out. Now, if I'm writing a single-threaded program, and I put in to write a log file, what's going to happen is I'm doing stuff, going, writing a log file, doing stuff, going, writing a log file, doing stuff, going and writing a log file, doing stuff, going. I'm always having to pop back and write things to the log file right in the middle of doing stuff. And while I'm doing that, I'm not doing stuff. So if I'm writing to a log file, I really don't want it in main in a single-threaded program. I don't have a choice if I write a single-threaded program. I live with it. And again, if the machine's fast enough for the complexity of the program, it's not a big deal. It's wasteful, but it's not a big deal. But if I'm trying to stretch everything I can, no bueno. I've already decided I need to write this as a multi-threaded program, so one of the first things I'm going to do is I'm going to launch a thread and have that thread write the log file. Now, main can do whatever it's doing. The other threads can do whatever they're doing, and the log file thread will just keep streaming stuff out at its slow, measured pace to the hard drive. All right. Seems like a no-brainer. So, in one of the textbooks, they said this is a perfect example for a detached thread. So what I'm going to do is this program, this lane here, this is doing all the work. Maybe I have some other threads that are doing work. But I launch off a thread down here, and this is my log file thread. It's going to feed out the data to the log file. And I'm not bringing anything back. So I'll save a few resources and say this is detached. So I launch it, and I say it's detached. Detached. I'm sure you can all read that. Now, this seems fine. Within the internal logic of the program, there's no real relationship here. There's no reason to bring anything back. I don't have to wait for it, anything like that. This runs and does its thing. This runs and does its thing. Everything's cool. But it doesn't take into account the operating system, and the operating system has its own rules, its own logic that can affect your program. Now, one of the things the operating system does, we talk about in the processes video, is it maintains parent-child relationship. If a thread launches another thread, the thread that did the launching is the parent, the other thread is the child. The operating system tracks this. One of the reasons the operating system tracks this is because the operating system does not allow orphan threads or orphan processes. No orphans. If the thread that launched another thread dies, it will track down all the children and kill them. And that is actually the code in Unix. You kill the thread. And it cleans up all the resources that that thread has. All right? So no orphans, no Batman. Okay? Now, imagine, if you will, this program's running along, it's doing its own thing. And then, boom, something blew up. Okay? Now, the first thing you're supposed to do, and no one does, but the first thing you're supposed to do is go look at your log file and see what it was doing when it blew up. All right? Catch the error, catch the thing that happened. All right? Well, if you go and look at the log file, which you usually don't look at until you've exhausted all your other options, but you go and look at the log file, it'll tell you what it was doing when it blew up, and you're like, oh, okay, I see it. I see where the error is. I see what the problem is. I need to change this in my code. Right? Or I need to file a bug. Right? Well, if I write the log file thread as a detached thread, boom, this blows up. This is writing the data out. Remember, I put it on there because it's slow, so it's delayed. It's got to write it out at the speed of the device it's writing to. So I'm writing out stuff, and while I'm writing out stuff, the operating says, ha-ha, orphan, execution, dead. Guess what? I just killed it, cleaned it up, and it never wrote the error. So I just went and wrote tons and tons of log files, and the one time I needed it, it didn't capture the piece of data that I needed. Why? Because I wrote it as detached, not understanding orphans got to die. Operating systems are really cruel. There's all kinds of terminology in it that's like, really? Okay, let's go kill some orphans. Yay. Do not take that quote out of context, audience out there. I can just see it now. That guy hates orphans. Only orphan processes, and it's not me, it's the operating system. Now, let's say I wrote this, and instead of making it attached, I went to the very end of main, and I put my join in at the last statement. Now, I've burned a few extra resources, sure. But, boom, it blows up just like before. And the operating system suddenly throws on its villain mustache from the 1920s and goes looking for orphans. And it finds an orphan. But when it sees the orphan, because it's a joined thread, it takes pity and says, oh, poor little orphan, I'll wait until you're done with your work, and then I will kill you. So it lets it finish writing the log, terminated, cleaned up. Okay? I capture it. Again, it's a simple example, but it's an example of how understanding that logic is going to impact your program from the outside. And there are lots of things in the operating system that do things like that. Trylock. Sounds like a character from Star Trek. Trylock. Now, we said lock was the basic building block. We got all kinds of different parameters and ways that we can mess around with it and get different behaviors. Trylock gives us a capability that we don't have with the regular lock. Now, with a regular lock, I go and lock it. If I get the lock, I go in and I execute whatever it is I've locked. If another thread comes along and attempts to lock it, it'll get blocked and put into that waiting queue and do nothing. Okay? If I use a try-lock instead, the behavior is the same for the first one with one minor difference. I'm going to come and I'm going to attempt to lock it using the try-lock. If I lock it, I take ownership and I act exactly like I would with a regular lock. The difference is that when I take ownership, I am going to return a Boolean value. And that Boolean value is going to be true or false. If I got the lock, it's true. If I didn't get the lock, it's false. So the first thread comes in, gets the lock, returns a true. Now, that Boolean value being returned, I can do something with it. It's executable. That's the first difference. On a try-lock, instead of going immediately and being blocked or some other scenario, I can evaluate that variable first. And I might try to choose to do something because it returned true. Like so, for example, I return true, so I mark a flag that say I successfully went and entered that code. Okay? When the next one comes, the next thread tries to lock it, attempts to lock it using the try lock. It doesn't get it. Now, in a regular lock, it would go sit into a wait, but this time it's going to return a false. Again, I can evaluate that false and act upon it. So I can say, oh, he didn't get it. And I can do something. For example, maybe I branch somewhere else. Okay? You could imagine a scenario where I've got two functions. The threads, we have fun1 and fun2. The threads have to run both of these. So first thread comes in and tries to run fun1. It gets it. It goes inside and it's running it. It marks a flag that says 1. Right? It has a flag for 2. Right? Hasn't been marked yet. Thread 2 shows up. Can't get it. Returns a Boolean saying false, and the Boolean says, oh, you didn't get in here? Okay, branch and try and get in here. Oh, I did get in here. I have those two flags, same code, right? 1 and 2, I got into 2, so mark it. Run through the code. When I exit out, flag 1 still not set. Loop, try and get flag 1. When this exit out, it says flag 2 hasn't been gotten. Try and get 2. At some point in time, I've gone through both of them. I exit out, both flags are set, break. Out of the loop, go do something else. If I didn't have this, even though they're both running both of these, if I just use regular locks, One of them would lock this, all the rest would get blocked sitting back here, and no one would be able to move forward until this one. So by using this tri-lock, we're good to go. But of course the code needs to need it, right? I need to have an alternative that I can run. We can also do it for resource allocation. I need resources A, B, or C. If I don't get all of them, I can't do anything. So I'll try and lock A, B, and C. If I don't get them all, I release them. If I get them all, I use them. You can do that kind of stuff too. Automatic locks. There are a number of different automatic locks. Again, these are building blocks. They can be put together in all kinds of different ways. The two that we're going to be concerned with are lock guard and unique lock. Now, lock guard is basically the automated version of lock. Unique guard, unique lock, that's a special thing. I can do all kinds of unusual stuff with it. So we'll go ahead and start off with lock guard. Just like before, its whole purpose is to lock an area, a function, something, right? The difference being, whereas before I had to explicitly unlock it, if I'm locking a function or locking something that has a scope, if I leave that scope, lock guard will automatically unlock itself. That can make my life a little bit easier. So let's say I want to lock an entire function. So first line in the function, I put in a lock guard command. That's it. That thing is now protected. What's going to actually happen is when the compiler looks at it and sees the lock guard command, it's going to go, oh, I need to lock this mutex. It's going to actually put the code for locking that mutex into the constructor of the function. So when I build the function, this will be locked when the thread calls it, right? Because it's in the constructor, that means its counterpart is automatically placed into the destructor. When I leave scope, finish the function, I call the destructor, and the destructor has the unlock built into it. Boom, it's unlocked. I didn't have to write an exception handler. The reason I didn't have to write an exception handler, I'm running through the code blows up. First thing I'm going to do is call the destructor. The unlock's already built in. So if I'm using a lock guard, I don't have to worry about writing an exception handler. That's kind of nice. The downside, in its simplest form, is it's an all or nothing kind of thing. I'm either locking the function and then unlocking the function. Right? So let's say that I've got a function and that function has 10 lines in it. Only 2 of those lines actually need to be controlled. Well, if I use a lock, a regular lock, and lock and unlock, I can go and lock and unlock those 2 lines. And the things can run in parallel in the other parts. So only those 2 lines are being locked and unlocked. But it's only 10 lines of code, so it's not that big a deal. It's pretty small. My improvement is pretty small. Might not be that worried about it. If I use a lock guard, it's going to lock the whole thing. All 10 lines get locked. There's no parallelism happening inside that function. It's one at a time. Lock it at the beginning, unlock it at the end. Again, if it's 10 lines and 2 of them needed to be controlled, it's negligible. It's easy peasy. Make my life easy. Just put it in there. Don't worry about it too much. I'm good. What if it's a function that has 800 lines of code in it and 2 lines need to be controlled? Do I want to lock 800 lines worth of code and make that whole thing basically serial because there are 2 lines that need to be controlled? Probably not. So where you use a lock guard depends upon the scenario. You know, how much is going to be locked? How long is it going to be locked? How does it compare? Right? If it's 800 lines of code, and in all honesty, all 800 lines of code, or 700 of them or whatever, all need to be controlled through this part, okay, lock guard's fine. Otherwise, I probably just want to use a regular lock and unlock. I have a lot more versatility with a regular lock and unlock. I can define exactly how much I'm locking and unlocking. With lock guard, it's not quite as refined, but it's easier. This is the exact same thing we had before, but instead of using lock and unlock, I'm going to use a lock guard. So, thread, string, vector, mutex, none of that changes. Declaring a mutex called mutex1, none of that changes. The way I launch it doesn't change. The way I join it doesn't change. The only thing that changes is up here inside my function. Before I start printing out hello world from thread, I put in a lock guard. Now you'll notice the syntax is different. Lock guards actually give us the automation, but they also give us some capabilities that we don't have with a lock. It's another reason that they're useful. So syntax here, lock guard, all right, that's what we're doing. Using a standard mutex, guard1. Guard1, what's that? And then in parentheses, mutex1. Oh, that's my mutex. What's that all about? Well, when we use lock guard, we don't actually lock and unlock the mutex. We create an instance of the mutex, give it a name, lock guard in this, or guard1, I'm sorry, in this case, and that's what we're locking and unlocking. So the thing I'm creating is an object, it's called a lock object, named guard1 using mutex1 as its pattern. Okay? If I'm just using regular locks and unlocks, and my code needed 10 mutexes, well, locks and unlocks use the actual mutex, so I would have to declare 10 different mutexes. If I'm using a lock guard, I can declare one mutex, and that becomes the model, and then I can basically on the fly create as many as I need. I just have to give them unique names. Guard1, guard2, guard3, guard4, and so forth. Or however I'm going to name it. I have to remember though, if I want to do anything and control it after the fact, I need to use the instance name, not the mutex name. Because the mutex is not actually being locked and unlocked, it's just being used as the model to create the instance that I'm using. So if I need to control this in some way, I'm going to use guard1. Okay? In this particular case, all I'm going to do is lock the mutex, right? Create guard1 and lock it, the instance of the mutex, I should say. And then I'm going to print out my hello world from thread, right? So I'm going to send to the screen, hello world from thread. This thread says, whatever I tell you to do next, do it to this thread and this thread alone, the one that's reading and writing the code this moment. And then get ID. Get ID basically says, hey, there's an ID number that represents this thread. Go find it and print it out or use it. Every thread gets a unique number that identifies it. It's how the OS knows them. Right? You can call it whatever you want to. The OS identifies it by the number it assigns to it. So this would say, hello world from thread 7752. Hello world from thread 7789. It's going to loop through that for each thread and print out 5 times hello world, hello world, hello world, hello world. When it's done, it returns to the join. Press enter to continue. Okay? Again, I didn't have to put anything else because when it leaves the function, it exits scope and it automatically unlocks. And that's probably the biggest trick to these is making sure you fully understand when it's going to leave scope and when it doesn't. Because if you don't have that in your mind correctly, it might unlock when you don't want it to, or it might not unlock when you want it to. That brings us to the unique lock. You declare it the exact same way. You just use the command unique lock. It works exactly the same way in that it creates an instance, a lock object that you're going to control. But it works with other parameters. And some of the things it lets you do deferred locking. That basically means I'm going to set the lock up, but I'm not going to actually lock it now. I'm going to wait and lock it later. There could be a number of reasons to do that. Maybe there are a lot of other things going on at this moment, so I don't want to lock it now because it'd be just too much happening, so I want to wait till later when it's calmed down, and I don't need it to be locked at this moment. Or maybe I'm going to branch and I only want to lock it if I go down one particular branch of code. Or maybe I want to lock it in different ways if I go down different branches of code. That's deferred locking. Timed lock, that basically says, hey, this thing, if it isn't done within 800 milliseconds, something's gone wrong, unlock it. This to allow recovery if something was to hang. All right. Recursives, the one we're most interested in is transfer of lock ownership. We say when we lock something, the thread takes ownership of it. It's the only one that can mess with it. What if we wanted to be able to transfer temporarily that ownership to someone else? That's what this allows us to do, and it's actually what we're going to use it for mainly in this class. In order to do that, it works in conjunction with another command, wait. Now wait, basically, as your thread comes into a function, let's say, and we're using a unique lock, thread 1 shows up, locks it, everybody else gets blocked out, it starts running through the code until it hits the line with the wait. When it hits the line with the wait, it goes into a wait state. It gets put into a waiting queue, and it no longer is executing any code. Well, the only reason I couldn't have more than one thread in there was because there were shared resources, and we didn't want them changing stuff at the same time. But this thread is now in a wait state. It's not changing anything, so it actually would be safe for another thread to come in and go through that first part of the code. So what ends up happening is the thread goes into a wait, it unlocks the lock guard, allows another thread to lock it, come in, run through the code, go into the wait, which unlocks it and allows another one. So what's going to end up happening is all of our threads are going to run through the first part of the code and stack up at the wait in an active state. What they're waiting for is a signal to say to them, hey, it's time to stop waiting. That signal is sent from another thread through the condition variable. I declare the condition variable. When I trigger it, send the signal, that tells all the threads that are waiting to wake up. Okay? I have to tell it what I'm locking and unlocking. That's the lock object, in this case, guard 1. And then I have the predicate. The predicate is an optional command that isn't actually optional. If you leave it off, you will not get an error. It will compile. It will run. It may run fine. But you have left yourself open to a bug, a synchronization bug. Now you would think that if I pile a bunch of threads up in the wait, that they would stay there until signaled to wake up. And that seems logical, but it's not the case. There's a thing called a spurious wake up. It's a bug. It's been around so long, it's a feature. And basically, and this took about a month's worth of resources to boil down, the simple version is In order to prevent deadlock inside the hard code inside the CPU, we have to have some mechanisms that trigger if we think that deadlock has occurred. We'll talk about that more later. If that happens, there's this kind of series of reverse Plinko machines that bang, 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 bang up through the code and will cause this to wake up even though it hasn't received the signal. What the predicate does is it evaluates to a true or false. It can be anything. It can be a variable. It can be a calculation. It could be a lambda. It could be a function. All it has to do is evaluate to true or false. When I receive the signal, hopefully through the condition variable, I'm going to check the predicate. If the predicate evaluates to true, I move on and wake everybody up. If I receive the signal, check the predicate, and it evaluates the false, I ignore the signal and everybody stays in their waiting state. Okay. So what you do is you set the predicate to something that is only true when this should be waking up. That way, if you get a spurious wake up, it says, oh, is the predicate true? No, it's not. Ignore it. When you get the actual signal, you should have changed the predicate, and it says, oh, should I wake up? The predicate is true. Yes, I will wake up. And it wakes up all of the threads. I said we signal it through the condition variable. We are going to declare the condition variable. Again, the condition variable is going to be in another thread somewhere else, sending the signal that says to wake up. How do I do that? With the notify command. There are two forms of notify, notify one and notify all. We're usually going to use notify all. Notify one says, I want one of the threads that's waiting to wake up. Notify all says, I want all the threads that are waiting to wake up. Now, real quick, what usually ends up happening is if I have a scenario where I want to wake up a thread, change some things, wake up another thread, change some things, wake up another thread, I put it into a loop and use a notify one. If I just want the threads to come out, notify all. Now, if I get the signal, notify all, I want all the threads to come out, we're still inside the mutex. So they actually can't all come out at the same time. What's going to happen is one of the threads, randomly, will come out, lock the mutex, run through the code, leave the function. That will trigger to unlock it, which means another one will lock it and come out. Unlock it, lock it, come out, unlock it, lock it, come out, unlock it. So they'll all come out very quickly and move on, but not at the same time. Yes, sir?
For the notify one, can you notify a specific one, or is it
No.
kind of like starting where it's just a random one?
It's just a random one. You have no control over it.
So where's the biggest use for notify one if you can't pick which one gets notified?
Well, it's not about that. It's usually about some sort of other configuration that you want to happen in between them. Okay? All right, we need to run through this real quick because we are running a little late today, but I need to get it all on the video camera. All right, so here's my example. We've included mutex, condition variable because we're going to use a condition variable, thread because we're going to use threads, chrono because we're going to use some time, and vector because I need to manage my threads. We'll start on this side. Here's our main. Oh, let me change that. Actually, look, we have declared a condition variable named convar, a mutex called CV mutex, and an integer x that is equal to 0. Now, going into main, first thing I'm going to do is I'm going to create a vector named threads. I am going to push 4 threads into it, and I'm going to send them to the waits function and run that. Next thing I'm going to do, I'm going to launch a single thread named sthread, and that single thread is going to go and run the signal function. And then I join the vector and the single thread so that main, after launching them, does not go here. Okay? So main is now idling here. Technically it's here and then it'll be here. All right? Let's go ahead and follow my 4 threads. So the first thread's going to come over here. It's going to enter into waits. It's going to put a unique lock on the mutex, or the lock object, I should say, called locked. That's the name, based off of CV mutex. It's going to print to the screen waiting. Now, when it made that lock, all the other threads, the 3 other threads, are all waiting to get in. It prints out waiting to the screen, and then it goes into the wait on the lock object locked, monitoring con with a predicate of is x equivalent to 1. Okay? When it goes into that, the function unlocks, the next thread comes in, prints out waiting, goes into the wait. Next one comes in, prints out waiting, goes into the wait. Next one comes in, prints out waiting, goes into the wait. So now I have 4 of them stacked up at the wait. In the meantime, the signal thread came over and entered into the signal function. And the first thing I did is put it to sleep for a second. Why? To make sure that all that other stuff's already happened before it goes forward. I want all the threads in the wait state before I start sending any signals. Okay? There are better ways to do this. This is just quick and easy. So I make it wait a second. That should be more than enough time. It then prints out notifying. It's going to send a notification. And then I notify all on convar. That sends a signal through convar to the wait and says, hey, I want these things to wake up. The wait will then evaluate the predicate. Is the predicate true? No. The predicate needs to be 1. It's still set to 0. The signal is ignored. They remain waiting. I go to sleep for a moment, again, to allow this to all settle through. I set x equal to 1. I print out notifying again. I send the signal, notify all. This time, wait receives it, evaluates the predicate. It is true, so it activates and starts releasing them. And the first thread, don't know who, first thread rolls out, locks it, prints out finished waiting, exits, goes to the join. The next one, finished waiting, exits, goes to the join. Next one, next one, next one. They all come out. They all go to the join. When they all hit the join, we move past the join, we hit this join. Well, by then, this is already returned, that join's already satisfied, so we move past it. Press any key to continue. Okay? See how that works? Visual Studio has tools built into it to help you diagnose problems with multi-threaded code. They are hidden and usually not easily found. There's an excellent, if you follow this link, excellent article on where the tools are and what they do. It's a good tutorial. Okay? Questions, concerns, issues? Excellent. All right, guys, we got to clear the room. I'll see you on Thursday.